What's up, everybody? This is for Calc 3, Calc BC. We're talking about series. This is section 5.2 out of our curriculum right now. There are the time codes. Go ahead and use those to skip ahead to the questions that you want to take a look at and maybe save yourself the chance of not going through every single minute of this video. We'll start with section 5.2, number 85. The question was asked, given this information we know about a series, like the summation of a sub n equals 1 and the summation of b sub n, it's in the video there. The point is, what can we do with that information? Some things to remember is that you are able to build out a sequence, or you're able to talk about splicing a sequence, or separating it by its pieces, and then adding, like, from a certain index on, like from 2 on, the information that we have. So what you'll notice here is that we already are given the fact that we're trying to determine the summation of the series from 2 to infinity. But if we think about what we knew from Calc 2 and integrals, we can apply that same conversation because they're integrally related. We'll get that word right, but the pun is intended. The point being that if we start from 1 to infinity, all we really have to do to go from 2 to infinity is just take care of that first term, that first element of the sequence, which is part of the overall series. And then isolating the summation, we're able to put the summation from 2 to infinity as the answer to this equation. And so that's all that's really happening right here, is just subtracting or evaluating where we put on the correct side. Let's see, is there an additional weird negative here? Yes, I'm sorry, I did catch that typo there, that right O, if you will, that the summation of a sub n and b sub n is its own calculation. Okay, next one is from 5.2 as well. All of these are from 5.2. And in this, we're talking from number 90. We're looking at the way that we can define, like, specific elements, or specific, elements is the right word, but pieces of the sequence that is then summed up to make the series. We kind of look at partial sums, like we look at the partial sum of 1 and then 2 and then 3, but we're trying to figure out a way to define, like, is there a relationship that happens between those sequence elements? Like, how is 1 and e over pi and e squared over pi squared related? And turns out it's actually e over pi is its own thing. Let's group them together. And then the exponent, the only way you're going to get a 1 and then an e over pi and then an e squared over pi, etc., is if the exponent of e over pi is 1 minus n, or, well, that seems a little weird. Is that right? It's there's something wrong with that example. I think it should be n minus 1. It'd be n minus 1, but maybe there we go. We make the fix right there. It should be positive n and a negative 1, so that your index, as it moves forward, 2 and then 3 and then 4, the exponent on each of those pieces are still 1 less. Now, does this converge? Well, we know that, for example, the sequence 1 over 2 to the power of n converges to 1. So if that happens, and this has the same structure, like the number on top is smaller than the denominator, the number on the bottom, and if that's the case, that fits a certain requirement that we have. We might call it R, or some other, not constant, but just growth factor, that if it's less than 1, then the whole series will converge. A convergence test. That's for a later section, but that idea. Next up is 5.2, number 93. And if you've skipped over a lot of the other, like the previous 2 questions, totally fine. Get here, get to the answer. Of course, this is one of those questions that is in the back of the book, or linked by the helpful hyperlink text that's in the section. We start by understanding that if we're trying to recursively define the elements of this sequence that are then summed up to make the series, some of the operations we want to do with an element, like a sub n, we can isolate a sub n plus 1. That's the goal. If you can define or isolate an element a sub n plus 1 to be equal to some sort of recursive formula, then that lets us start to generate sequence elements. And in generating sequence elements, then we can start getting to a formula, an argument of the series. Like here we have 1 over negative 5 to the n minus 1 power. This looks very similar. It's an oscillating, goes back and forth between negative and positive, negative and positive. So to force it to be an oscillating result as we plug in like 1 or 2 or 3, etc. for the exponent, we do need to pop a minus sign in front of everything that's there. Always, please, feel free that you can just put this thing on mute and you can drag the slider on the video so that you can skip to whatever you need to do. You can put it on pause or, listen to the recording at a slower rate just to give you a chance to process. With most math videos, if you're looking for help about how to do them, you should be trying to also capture or comment, like record on your own paper some information that we have. Here's that comment from maybe previous question, but also applies here. The r, the thing that's inside the parentheses and raised to a power of n minus 1, etc. The minus 1 because of the index n equals 1 to infinity. But if that's less than 1, if the absolute value of it is less than 1, then the series converges. All right, now we're on to number 94. In number 94, can we figure out a way, just like number 93, to rewrite or re-express this relationship, this recursive definition of how a sub n and a sub n plus 1 are related? If we can solve to make it be a sub n plus 1 equals, then we have a way of defining the first term, the second term, the third term, the fourth term, and so on. And we do, and we realize that that is actually a divergent series. Sequence also applies. Okay, number 5.2, section 5.2, number 99. And maybe it's already up on your screen, but I just want to acknowledge you've jumped in at the right time code if you want to see how to do number 99. 11 minus y equals the summation from n equals 1 to infinity of y to the power of n. I think I read that right. Go back and see if I did. But point being is we have this expression, right? We have this expression. This is actually the definition for us. Through processes that are on a different video and in a different part of our class period, or even just in the text, we came up with, or will have come up with, this relationship of 1 divided by 1 minus y is equal to the sum of y to the power of n, starting with 0, working forward. This one took a little bit of time. We worked on it for a while. In fact, it might not even be fully contained in this video. It might be on another video that you should go find that also explains this simply. I hope it's here, but honestly, I don't think it is. I think it's on another video because there was a moment of brilliance that happened. And what you're seeing right here is trying to get to that moment of brilliance. And like a lot of math situations or puzzles during this time, things are not going to be easy. The type of math that we have is asking you to call upon the broad and diverse spread of everything mathematical that you can now use as a tool. Maybe some minor 1-week exploration in Algebra 1 is what's necessary for you to be able to come up with an answer. What is the locking mechanism that brings this whole thing together? Linchpin, they might say. My camera did have some glitchy moments, so what we're seeing is a 30-second or so some odd interval of what's happening in between. So we tried some trig identities, like how sine squared plus cosine squared of theta or of x or whatever equals 1. That didn't work. We weren't able to get to the negative. We tried isolating. We tried, multiplying through the whole thing by -1 and forcing the sine squared of x to be negative. But then that also forces the 1 to be negative. It doesn't quite get to the 1 minus y structure. Key in on that, it doesn't get to the y, the minus y structure. We tried some other things. We thought, well, if this is technically a definition or it's an identity, then we should be able to maybe multiply both sides by 1 minus y, or we should be able to multiply by 1 plus y over 1 plus y. Some sort of binomial conjugate happens. That gets close. That's not bad. That was a really good direction to take this question, but it's not right. And we ended up looking at the answer in the back, in the hot links, and figured out that it needs to be -1 to the n. This is referring to the argument. -1 to the n power multiplied by sine of x to the 2n power. It's still working through what's the one thing that we need to do? And we spent some time on this in class, in our discussions to try to get there. And again, I'm just reminding you, remembering that day, that moment, we didn't get to a solution, but we were trying. We were trying all sorts of, the analogy being spaghetti that you throw against the wall to see if it's done. Cooking technique from somewhere, I don't know. But the point is, if it sticks, use it. And we were trying different techniques from Algebra 1, Algebra 2, pre-calc, even thinking, were there any calculus tricks that we could have used in order to get to this simple substitution. You know what? Ultimately, we walked away from it. Oh, bonus for you. I got 5.2, number 102 for you at 10 minutes. This is a telescoping series, but what they want us to do along the way is try to figure out how it spreads out and then what it collapses back down to. Again, the video is so glitchy. Thank you. I'm so sorry about that. But what I want to acknowledge right here is that we are able to have that conversation of how we can build out the first, second, third, fourth K partial sums. And in building out the K partial sums, oh, we're back to 99 again. Okay, let me finish the last comment. Yeah, you can see that things collapse and you're left with the final thing with K in it. Okay, back to this one. We're still trying to figure out a solution for number 99. I wanted to emulate that. Sometimes you try a problem, you work it through as much as you can, and nothing happens. You don't even make good progress. So you don't delete your consciousness about it, but you go search up a solution, or you talk to someone else, or you try to do, a little bit of research to see if you come up with a solution. And then if you still don't, put it down. Don't actively write and try to solve it. Actually, just put it down and walk away. And in doing that put down and walk away, sometimes you get that moment of brilliance that says, that's the key trick. We never get there at this one, not in this video. It's in another one, but there's a substitution that's really simple that all you got to do is sub done. Seriously. Check that other video out. Hey, we're looking at number 116 now. I believe number 116. Maybe this is there are so many things that we talked about. I try to compress them all. Long video. If you are still watching this whole thing through, bless your heart. That's amazing. And also, why? Didn't you just use the time codes? Okay, this question, Leaning Tower of Liar. Some good videos online, some good resources online that were used to help us get to a solution. The first one being that, is it Michael from Vsauce and Adam Savage from Mythbusters, or now his new show, Adam Builds, where he does one-day builds. They did a build of these blocks, and then they actually generated a really, really expansive Tower of Liar. And the truth behind it is that the relationship, your center of gravity changes by what we call a harmonic series. So again, feel free to Google that, look that up. And in our harmonic series, we're able to define the relationship between each successive step to its previous. And if we are, assuming that this Tower of Liar extends off to infinity, then we have a series, an infinite series, but we can generate a sequence of partial sums by just stopping the tower at a certain spot. So maybe we stop it after, well, here we have after 3 steps. But our conversation in that class was what it was. I realize now the video has ended. If you are still watching, thank you so much for putting the time in to see it. I hope this helped. If anything, make sure you can give me a comment or a message or a chat. And thank you for watching this video. Check out the other ones for any extra help along the way. Bye.